We don't hear you, Rita.
Oh, sorry. Okay, I just say that was very nice music to introduce our last invited speaker of this CAR 2022. And again, it's a place for me to introduce Diana. I can talk about Diana for long time because I met Diana when she was a student, and I see how Diana was grown from a student to an actual professor in our faculty. Diana is always worried about everything that has to see with the students, with the didactic problems. And I think that she participates with CAR every year to the beginning, maybe. And so we are really, I think that in particular, Magdas and me, that was the first organizer of this CAR. We are very happy that now you are our invited speaker. So thank you very much, Diana, and the time is yours.
Thank you very much. You can hear me clear? Okay.
Yes.
Let me share my screen. So you can see it now.
Yes.
Full screen? No?
Now it's okay.
Okay. So I will talk, well, first, thank you for the invitation. I will talk about, let me close this thing. I will talk about Euclidean rhythms. They are related to music patterns and polygons. So we know mathematics and music have been related for over 2,500 years since Pythagoras developed a musical theory based on ratios of small integers. And there are many studies about mathematical studies related to music, about scales, but not many about rhythms, about time duration intervals of rhythms. So I will talk about how the classical Euclidean algorithm, which is used to obtain the greatest common divisor of two numbers, defines a family of rhythms that appear in many music around the world. And this algorithm is also related to other interesting problems. So we can see a musical rhythm as a two-way infinite binary sequence. In this sequence, each beat represents one unit of time. We call it a pulse. And we represent a played note. We call it an onset with a one beat. And we represent a silence with a zero beat. Usually we have cyclic rhythms, which are patterns that are repeated throughout a musical piece, and we can codify them by an n-bit string of zeros and one. Actually, there are different representations of cyclic rhythms of n pulses. First one, the one I mentioned before, as a binary sequence. We have an example here, 16 pulses and 5 onsets or played notes in these positions. So we put a 1 for a played note and a 0 for a silence. It's also useful to write an X instead of 1 and a dot instead of 0. Visually, it's more clear. This is called the box-like representation. So here we put an X instead of 1s and dot instead of 0s. And we have another representation of that rhythm. We can also codify rhythms by writing the distance between two consecutive onsets. For example, these two are at distance 3, 1, 2, 3, distance 3, 4, 2, and 4. So we write it in this way. This is a nice representation. It's indeed a partition of the number 16, the number of pulses. So here's the example I mentioned. Let's hear it. We have 16 pulses and these 5 played notes. And this rhythm appears in several music. It is the Cuban clavecin. Let's hear a little bit of El Cuarto de Tula, played by Buena Vista Social Club. Let's see if you can identify the rhythm we heard before. There's another nice representation of rhythms, the clock diagram representation. We can put endpoints equally spaced around a circle. We start here and time flows in clockwise direction. This is the rhythm I mentioned before, the Cuban clavecin. We join two adjacent onsets by a line segment. So we obtain a polygon representing the rhythm. We write numbers starting from 0. So in this case, the onsets are in positions 0, 3, 6, 10, 12. So we can also codify the rhythm by writing a subset with these numbers, 0, 3, 6, 10, and 12. Here we have 3 different rhythms. Visually, we can see that the one in the left side is more regular than the one in the middle, and this one in the middle is more regular than the third one. The rhythms have usually a colon-response structure. There's a rhythmic question, which creates musical tension, and there's an answer that releases that tension. In music, they use syncopation and accentuation to create that rhythmic tension. For example, if you have 16 pulses and we play 4 notes, we could distribute these 4 notes evenly, putting one note in position 0, another in position 4, 8, and 12, and we would have a regular rhythm. But if we decide instead to play 5 notes, we can play a note in a place where it is not expected to be heard. So here we play a note, it's not the place where we expect to hear it. Also here, we play a note, it's not the place where we expect it. So this creates a rhythmic tension. And then we make an accentuation, we put a note here in the place where you expect to hear it. So that releases the tension. So the idea is to evenly distribute onsets, but creating a certain contradiction with the underlying meter. And the question is, how can we then construct a rhythm of maximum evenness with k onsets and time span n pulses? Sometimes the answer is easy. We have the last example, 16 pulses and just 4 onsets. We can evenly distribute them because 4 divides 16, so we put them in position 0, 4, 8, and 12, and we have an even rhythm. This is because 4 divides 16. This is not the general case, but we see maybe the solution has a relation with the greatest common divisor of those numbers. Mathematically, the most interesting rhythms are then those with k onsets and time span n with k and n prime relative. Here we have a clock diagram representation of bossa nova and rumba rhythm. We can see that bossa nova is more regular than rumba. We have indeed different ways to measure evenness in rhythms. One measure they use is to take the sum of geodesics along the circle between all pair of onsets. So for example, we have these 2 onsets. They are at distance 3. This one and this one are distance 6. So we take all distances between onsets and take the sum. In some cases, this can detect different rhythms. But for example, for bossa nova and rumba, if you do that, you obtain number 48 in both cases. So it cannot distinguish certain rhythms. We can take another measure. We can take the sum of chordal distances between adjacent onsets. So we take 2 adjacent onsets and we measure the usual Euclidean distance between these two points, and we take the sum, and this is the other measure. In this case, then we obtain a greater number for bossa nova. It can be proved that the rhythms maximizing this measure are the same as the one maximizing the area of the polygon. There's another more discriminating measure, which is to take the sum of chordal distances between all onsets, not only between adjacent onsets, between all pair of onsets. And as mentioned, this is more discriminating measure. This is the best measure for evenness. So we see we have a mathematical way to measure evenness. So the problem is how to construct a rhythm which maximizes that measure. And the answer is in the Euclidean algorithm. Euclid lived around 300 years before Christ in Alexandria. Here we have a picture of his statue at the History Museum at Oxford. He was a Greek mathematician, geometer, and logician, best known for his work, The Elements, a 13-book treatise. This work includes geometric number theory and algebraic results. In the algebraic results we can find here, we have the Euclid's lemma, which is the basis to the fundamental theorem of our arithmetics, very important, and the Euclidean algorithm. which is used to obtain the greatest common divisor of two numbers. Here we have a picture of a painting from Giuseppe de Rivera, a Baroque painting, which is in the Getty Museum in Los Angeles. So let's remember how the Euclidean algorithm works. If we want to get the greatest common divisor of 28 and 6, we can think it geometrically. Take a line segment of length 28, a line segment of length 6. So the idea is to cut into pieces of the same length both segments. Obviously, this can be done. If you take pieces of length 1, we could cut both segments, but we can do it in a better way. The idea is to take pieces as long as possible. We know 6 times 4 plus 4 units equals 28. So if we are able to cut this blue segment and this yellow segment into pieces of the same length, then we could use that pieces to cut also the red segment. Algebraically, this means that the greatest common divisor of 28 and 6 is the same as the greatest common divisor of 4 and 6. 6 is 4 plus 2. So if we can cut into pieces of the same length this yellow segment and the green one, we could cut also the blue one and in consequence the red one. Algebraically, the greatest common divisor is the same as for the numbers 4 and 2. And this is easy because the yellow segment is twice the green one. So if we can cut into pieces of length 2 to these green pieces every other segment here. So the answer in this case is 2. And we obtain this number by subtracting to one number multiples of the other one in order to obtain smaller numbers until the result is clear. This process was named by the Greeks antanairesis, or successive subtraction. So Euclidean algorithm is this. It is based on the fact that the greatest common divisor of two numbers remains equal if we change a number for that number minus a certain multiple of the other. It's easy to show that because the numbers that divide A and B are the same that the ones that divide this number and B. So the common divisors of these two numbers and these two numbers are the same. So what we do is we divide A by B and change A for the residue of this division in order to get a smaller number. We do the Euclidean algorithm in several steps. We do some divisions until we obtain an exact division, and the last residue different from 0 here is precisely the greatest common divisor of A and B. So how can we use this Euclidean algorithm to obtain rhythms? In 2003, Forglund, I don't know exactly how to pronounce it, adapted the Euclidean algorithm to solve a problem in neutron accelerators at Los Alamos National Lab. Here we got a picture. In the problem, there was a timing system controls a collection of gates over a time window divided into n equal length intervals, and the system can enable a gate during any desired subset of the n intervals. So what he wanted to do was to distribute k pulses over n timing slots in the most even way possible, even in the case where k may not divide n. And he found the answer in Euclid algorithm. Let's see how it works. If we put 12 pulses and we want to distribute 5 onsets. Let's see an animation. I found this animation in the web page. Algebraically, we know the greatest common divisor of 12 and 5 equals the greatest common divisor of 7 and 5. So we put the 5 onsets in the left side and the remaining 7 pulses in the right side. We combine them by forming pairs. We obtain 5 pairs in the left side and 2 remaining pulses in the right side. Algebraically, this number equals the greatest common divisor of 5 and 2. And then we continue with the same process. We combine the objects from the left side with the objects in the right side, forming pairs. We obtain 2 objects in the left side and 3 in the right side. Algebraically, this is because those 2 greatest common divisor are the same, 3 objects and 2 objects. And finally, we repeat this process. We combine the objects from the left with the objects from the right, forming pairs. We obtain 2 objects in the left side and only 1 object left in the right side. So the process is done. We glue it all together algebraically. This is the codification, and we obtain a sequence in which we have these 12 pulses and the 5 onsets evenly distributed. In a box-like representation, the rhythm is this one. Here we have the onsets. So this is, I think, very clear visually, but there's a more practical way to do the algorithm. Let me put it the same numbers, 12 pulses and 5 onsets. We put a sequence of length 12, 5 ones and 7 zeros, and then we take the zeros, as many as we can, and put them under the ones. So we take 5 zeros, we put them under the ones. There are 2 zeros left in the right side, so we put them under the array, like this. There are 3 columns remaining in the right side. We can take 2 and put them under the array. And we've got only 1 column left in the right side. So the process stops here. And we read the numbers by columns from left to right, up and down. So we obtain the sequence 1 0 0 1 0 1 0 0 1 0 1 0. We write it here. And in box-like representation, we have this one. The rhythms we obtain in this way are called Euclidean rhythms. We denote in this way the Euclidean rhythm of length n with k onsets. So let's see another example. If we have 8 pulses and we want to evenly distribute 3 notes, we put a sequence of ones and zeros. We put 3 ones and 5 zeros. We take 3 zeros and put them under the array. There are 2 zeros left in the right side. We put them in the under the array, and there's just 1 column left. So the process stops here, and we obtain 1 0 0 1 0 0 1 0. This is a sequence. In box-like representation, we obtain this. It's a very easy rhythm. But it's important. It appears in many traditional music around the world, in particularly in West African traditional music, in Cuban music. It's called the tresillo, and in rock and roll music from the 50s. Let's hear the rhythm. We have 8 pulses, the 3 played notes. As I mentioned, there are several examples of songs including that rhythm. I chose one. It's the bass sound in a famous hound dog from Elvis. So let's hear a little bit. Let's see if you can recognize the rhythm we heard before. So let's see another example. Let's change it a bit. We have length 8 again, but instead of 3 played notes, we put 5. So we put 5 ones, 3 zeros. We take the zeros and put them under the ones. There are 2 remaining columns in the right side. We put them under the array. And we have only 1 column left in the right side. So process stops here. We obtain a sequence 1 0 1 1 0 1 1 0. And in box-like representation, we have this. We have evenly distribute the 5 notes along the 8 pulses. This also appears in music around the world. It appears again in West African traditional music, in rock and roll music, and in jazz. It's called the cinquillo. Let's hear it. It's 8 pulses and the 5 played notes. This is actually the clapping sound in Hound Dog from Elvis. But let me show you another nice example. It appears in milonga from South America. And let's hear a little bit of milonga criolla. This is a video I found on YouTube. It's a nice video because it's a video to learn how to dance milonga. So we can hear the rhythm. And in the last part of the video, we can see how dancers follow the rhythm. How they follow the rhythm, and the long steps. This is part of the rhythm. So I just put this few examples, but there are really many all over around the world having these Euclidean rhythms in the songs. Let me now talk about another contexts in which we can find Euclidean rhythms. If we want to draw the digital line, we want to convert a straight line segment into a sequence of pixels. Let's have an example. This segment from the origin to the point 16.5. If we can color the squares in this grid intersecting the line segment, we have this. So this sequence of pixels could be a good representation of the straight line segment. If we follow the upper boundary of this sequence, we have here 3 pixels, 3, 3, 3, and 4. This is precisely the Euclidean rhythm of length 16 and 5 pulses. Remember, we can qualify the rhythm by writing the distances between 2 pair of adjacent onsets. We have distance 3, 3, 3, 3, and 4. So we obtain the same numbers here. If instead we look at we follow the lower boundary here, we obtain 4, 3, 3, 3, 3, which is not the same as even, but it's a cyclic permutation of the same rhythm. So we actually obtain, this is obtained by an Euclidean rhythm. Another place where we can find Euclidean rhythms is in the count of time in calendars. We know a solar year is almost 365 years, but not exactly. It's a little bit more, almost a quarter day longer. So in our calendar, the Gregorian calendar, we make some adjustment in order to go synchronized with nature. If we don't do the adjustment, if every year we put 365 years, then natural phenomena begin to move along the year, and maybe we would have a spring equinox in June or things like that. So we made an adjustment. Some years we add an extra day. We have what we call a leap year. We do it almost every 4 years. We have a leap year when the year is divisible by 4, but not divisible by 100, and also when it is divisible by 400. So this works really fine, but it's not the only way to do it. There are many cultures which do it different. In the Jewish calendar, for example, they have a regular year of 12 months. In that case, months follow the moon, so they are about 29 days long. So their years are shorter than ours. And to make that adjustment, instead of adding an extra day in certain years, they add a whole month. So their leap years have 13 months. And they have a cycle of 19 years, from which 7 are leap years. So if we begin to count from year 1, the leap years are the years 3, 6, 8, 11, 14, 17, and 19. In box, like notation, starting with 1, we have a leap year in position 3, 6, and so on. So this would be the representation of how they distribute these leap years along his 19-year cycle. This is a cyclic permutation of the Euclidean rhythm of length 19 and 7 onsets. If you take these last 5 pulses and put them at the beginning, you obtain exactly the Euclidean rhythm, the corresponding Euclidean rhythm. I don't know exactly how they decided to put them in these places, but it turns out that this is a very good way to distribute the leap years along the cycle of 19 years. And it's precisely the way we do it by using the Euclid algorithm. So finally, I'd like to mention that it is proved that up to cyclic permutation of rhythms, there's only one rhythm that maximizes the measure, the last one I mentioned before. And it's also proved that the rhythm which maximizes that measure of a rhythm of length n and k onsets is precisely the Euclidean rhythm corresponding to those numbers. So finally, I give the reference. This is paper number 2 is the paper where you can find the proof of the results I mentioned at the end. This one is where you can find the animations I put for the algorithm. And if you look on the internet, you can also find many pages about Euclidean rhythms, because they are used to create electronic music, modern electronic music. They like to create music by using mathematical patterns, especially by using the Euclidean rhythms I mentioned before. So there are even apps to create music by using these rhythms. So thank you very much. I stop here. Thank you.
Thank you very much, Diana. Very, very nice talk, as always. I like a lot. We can recognize some of these typical tum 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 tum. So I don't know if somebody have some question, comment. No, I think we have a message to Hannah has to leave. Just 1 minute ago the talk, but she said that thank you very much. She enjoyed a lot. So I don't know if we have more comments. Maybe no. Okay, somebody of it's time to say goodbye. It's time to, okay, first to all, thanks again, Diana. Very nice talk. I don't know if somebody of the Polish team like to say something. No.
I don't know if Magda is here. Okay, Magda is here. Magda, maybe she wants to say something. But
yes, I would like to say a word, a few words of thank you for my students who decided to attend to CART, for Michał, for Hania, for Adrian, and also for Magda from Warsaw. I'm really very happy that you were here, and really thanks a lot. And of course, thanks for you, for organizers, and for everybody who gave a talk.
Yes, and thanks for all the invited speakers for very valuable talks and giving us a lot of inspiration. for the future work, and of course for all the Mexican organizing team, especially for Rita, Julian, and Naid.
Thank you very much. Okay, so Julian, I need the name of one person. I write you. Sorry. Okay, I just like to finish this card 2022, and at the name of all the organizing committee, I like to say thanks to all our invited speakers. I repeat that Magda says for their nice talk. Thank you very much. We like to say thanks to the rest of the participants with videos and posters, and all our followers in Facebook and YouTube. Thank you very much. And I think that the organizer committee gives a special thanks to Osvaldo Reyes for his help and support in the technology things. So thank you very much, Kiwi, the family name, the friend name. And finally, I'd like to say thanks to the great Mexican-Poland organizer team. Thank you very much to all. And see you next year, CAR 2023. Okay, thank you very much. See you next time.